My name is Dhruv. I'm a researcher in the Google DeepMind team. And as we'll talk about more today, I work on the Gemini Robotics team, where specifically I focus a lot on the actions part of the model. How do we take a big foundation model like Gemini and make it talk the language of the real world in terms of spitting out actions? And we have a notion of pre-training and post-training for these actions models that we call vision language action models, or VLAs. And I specifically focus on the post-training parts of the actions model.
My name is Ted. I'm also a researcher on the Google DeepMind team, focusing on robotics. My main area of work within the Gemini Robotics team is on the VLM side, so the embodied reasoning model. I think this is kind of just showing the core thesis of our team here at Google DeepMind, which is that robotics can and should be solved the same way that language and vision was solved, by using the same methods and techniques and philosophies that really looked into scaling data, understanding the world from first principles, and using that and applying that to generalize in the real world.
Speaking of, like first principles and understanding the world, so like as I understand with this new release, there are like two models, right? Like vision action model and the like this reasoning thinking model. As I understand, like the biggest novelty comes from this reasoning model. You, did I understand correctly? Just like wondering, like what is the new with this release that really kind of changed things, that really was in like, I don't know, innovative.
I think you hit it right. I think there's fundamentally the reason this Gemini Robotics 1.5 release is so exciting to us is that there's two primary top level takeaways. One is, I think we're starting to see that improved embodied reasoning capabilities, how these models can understand and think about the physical world in a way that's fundamentally different from reading PDFs or writing code or doing math. The physical reasoning capabilities of a model are driving a lot of the generalization improvements of our Gemini Robotics 1.5 model. But the second big hit is and maybe Dhruv can talk about this in a little bit. Is we've seen very promising signs using a method we've discovered called motion transfer, actual cross embodiment performance capability transfer across different types of robots. This is not a new idea. It's been a kind of very exciting direction now for a few years. But I think in the past, cross embodiment has always been kind of very shiny, very unknown, and with some kind of you can see like tiny slivers of why this might be possible one day. And we think now that that day might be here, where you can actually expect that data and knowledge and motions from specific robots, like a tabletop biarm robot, could transfer to other types of robots, like a humanoid robot. And we started seeing strong signs of that in this Gemini Robotics 1.5 release.
If you could elaborate more, like how does this work? So like is it like one system that controls several robots, or like how this transfer works?
Kind of like Ted mentioned, I think the spirit we're going by with here is how do we get this this scaling story to work in robotics, and to maybe trace the lineage of where we are in before talking about this new model, which is called Gemini Robotics 1.5. Earlier this year, we launched Gemini Robotics, which was kind of the first of its kind VLA model, which was trained on top of frontier model. And the way we and everybody else in the community kind of approaches this problem is you take a robot and you try to scale up your fleet of operations, kind of like we do in language processing in computer vision. So you get a lot of robots, you collect data on a lot of robots that you have, and then you try to teach specific skills to your models. And the big breakthrough that's happened in robotics in the last year or two is that once you know what kind of behaviors you want and you can demonstrate those behaviors to your robot, the robot can learn them. And that's great. We now have model architectures that can learn whatever we show them. And that was the big breakthrough that we
Is
kind of
it that you're referring to imitation learning, or?
imitation learning. That is
Mhm,
correct.
mhm,
So
mhm.
imitation learning based primarily on human teleoperation. And that is kind of the big source of teaching a robot what to do, which is kind of what kickstarted this whole movement that we're seeing around us of end-to-end robotics. The new thing that has happened with this 1.5 release for us is not only can we do that, we can keep training and keep teaching more skills by showing them on the robot that you have. We have a couple of things here. One of the things which Ted mentioned, which is motion transfer, is the fact that not only can you teach one robot by showing it what to do, but you can actually do that on multiple different robots and they help each other. So the way this would work kind of in abstract is, let's say we have three different types of robots, and we have a humanoid robot, we have like a tabletop robot, and we have like a different tabletop robot that can do industrial tasks. And each of them, you grow their fleets and you teach them new tasks, and as we've seen before, they can learn these new tasks from demonstration. But with this new idea and a few different algorithmic losses and architecture things, once we train this big model across all of these, let's say three robots, not only can they each solve the task they were taught, they can actually teach each other. So there is the sharing and transfer of the motions and behaviors that they've learned. And that is new because that kind of opens more doors onto what it might mean to scale robotics. I don't just need to scale up robots in my warehouse in a corner of the city. I can actually scale up across different robots, and different robots can teach each other. That is kind of one big thing that changed for us, and we want to keep understanding why and how we improve on these things. The second thing, which I'd also talked about, was trying to bring the VLA to look more and more like Gemini itself, like a VLM itself. And towards that, one of the things that was new in this release was this notion of interleaved thinking, or thinking before the robot acts. And what this kind of looks like is you have this VLM based robot model that can take actions, but every once in a while, it can actually also speak, answer text. So when it's trying to solve a task, it's actually thinking in text when it's solving. And this is kind of very similar to how reasoning models in LLMs, now we've all become used to thinking models, as we call them. And what that looks like is, if you're given a hard task, they would first break the hard task down into smaller things that you know that the policy can solve. And then once you break it down into sub steps, or once you check that, oh, I think I failed when I was doing that, let me try again. When you make the model speak both text and actions, you bring it closer to what the base model understands, which is text and images. So we have the first signs that actually interleaving text and actions actually leads to a better actions model. So as we go forward, we're going to try to make our actions models closer and closer to the base model, which is Gemini, so that we can learn from the base model's capabilities.
But when you say the robots are learning from each other, you're saying they have a common shared memory, right? Like that.
What I mean by learning from each other is, let's say in your training data, so not during inference, not watching each other, but in your training data, let's say you have a humanoid and a tabletop robot, and you taught the humanoid to pack a suitcase, and you taught your tabletop robot to assemble this industrial tool bed with a timing belt on gear belts. Once you train this model, your humanoid can do the timing belt task, and your tabletop robot can do the suitcase filling task. And that is kind of what I mean. Like you demonstrated the task on one of the robots, and you train the model across both the different robots, so the new robot can also solve the task that it was never demonstrated to solve.
If it would be useful to also, Dhruv, if we can give some background on kind of where the robotics landscape is today and why this is so exciting to us as insiders. Right now in the ecosystem, right, I think there's a lot of hype and excitement. I mean, that's why we're here and wanting to share this energy with you. But you see exciting, like a 1x announcement this week, or you see amazing Tesla and Figure demos, and you see a lot of startups and companies and really cool research from our friends across the community. Maybe you've seen like Generalist AI or physical intelligence, a lot of really cool research and a lot of cool videos. But I think under the hood, there are some fundamental bottlenecks that everyone inside right now knows. It's the elephant in the room, that there are major kind of unknown technology innovations that still need to happen if we want general purpose robotics to be all around in society, helping us, being deployed in our homes and restaurants and factories. There are still fundamental AI kind of breakthroughs that still need to happen. The way that almost all of the videos you see today are happening under the hood is a lot of data collection where companies are paying human operators to collect data, like pilot the robot, teleoperate the robot with something like a VR controller or something like that in their office, in their warehouse, on their robot. And they collect a ton of data of this type. And then they use that to train AI models, neural networks to imitate that kind of behavior. at least for manipulation. And then for like the walking and dancing and kung fu, that uses simulation a bit more because it's an easier problem where you don't need to be constantly in contact with the real world with cloth and deformables and rigid objects. Generally, for all of like the nice manipulation demos that you see, that's all being powered by very expensive large amounts of data collection on your robot in your warehouse that Dhruv was mentioning. And so I think the holy grail that everyone in the community is chasing right now is how do you get a truly scalable way to actually collect an internet of robotics data. And I think there's a lot of ways to do this. You can think about learning from human videos or learning from world models or simulation or there's a lot of ways you can do it. And I think a lot of them are promising. But the breakthrough that Dhruv and I have been very excited about for Gemini Robotics 1.5 is the ability to scale to data from other robots. So you don't just have to collect data on your robot in your office and paying someone to kind of do that. And then if you switch robots, you're out of luck. That's the context of why we are so excited. And we think that this is the most exciting sign we've seen that this actually works in the last 2 years or so.
I'm just wondering, are there like limitations, like types of robot that can share, or like different types of robots can like easily share that knowledge with each other? Like, I'm just like wondering with this, if there are like any limitations in this approach.
I should have started with the statement, well, this is like active research and that this is the first time we've seen these signs. What we have been able to see is we have three embodiments in-house that we focus on. A couple of tabletop bimanual robots and a multi-fingered humanoid robot. And we have been able to see transfer between them. There's a lot of ongoing work on trying to figure out how much we can push this. As a lot of people might be aware, there's interest in other startups that want to sell data. So people want to collect data in what's called a data foundry, and then you can just buy data. Can we use that? We don't know. We haven't really kind of fully proven or disproven how useful that is at the moment. Similarly, can we scale up human data? Can we scale up learning from videos and other types of robots? So all of this is kind of still new. And I think what we shared so far is just kind of how far we have gotten in this journey. But there's a lot of different avenues where this, I don't think we solve robotics till we scale up this problem, because robots will keep getting better as we see. Between today and 2 years ago, the landscape of robots looks so different. A newer version of a robot is significantly more capable than the last version. And if we need to start from scratch to collect data on every new robot that we build, that is just not a very good way to, not a feasible way to get there. This is something we are really very actively looking in. And hopefully in the coming months and years of research for us is to best leverage different, how can we learn from different versions of the robots, but also completely new robots, which might have new capabilities that the target robot that you care about might not have, but it's a lot easier or a lot cheaper or a lot faster to teach those to certain robots than other robots.
Ted, when you said like addressing like elephant in the room, is it only comes down to, or mostly comes down to data collection, like high quality data collection, like when we talk about the advancements in robotics, or there's something else, some other obstacles, like on the path to generalization?
I think maybe also here to give context, I think a few years ago, everyone in the field thought that robotics was very far away, that we'd have to have significant algorithmic innovations, data innovations, and new hardware in order to solve robotics. I think where we are today is that there starts to be, very reasonable beliefs that we are very, very close. I think very smart people are saying that, we'll have general purpose humanoids in all of our homes next year. I think that's a bit fanciful, but I think for I would say a lot of the median robotics research today knows that there's still fundamentally substantial unknown research that we need to solve as a field before that dream of ubiquitous robots is actually going to happen. I think though the role of are we just missing the data? Do we have everything else and we just have to go and collect an internet of data and then just do what language models did and then just apply it to this new internet of robotics data and then we're there? Or is robotics a special problem and requires new breakthroughs that treat the physical world differently than how you might treat the digital world? Broadly, I think that's the elephant in the room of what is this problem we need to solve? And will scaling the data be enough? And I think there's a lot of folks kind of all across the map with where they stand on this belief system. Most people, I would say, agree that collecting substantially more data or unlocking the ability to learn from more diverse data is definitely necessary. And whether or not it's sufficient, I think, is up for debate. But I think most people are agreeing that it is necessary.
Even like for researchers, it's not even clear what other bottlenecks might be. Collecting the diverse data is extremely useful. We see improvements, but like once we go through that path, there are like more and more challenges might be unlocked that we're not even aware of at this point. Can you please elaborate in like with these like two models that work together in some applications, some use cases, where that embodied thinking model applied to complete the task?
Maybe I'll do a clarification and then I'll hand off to Ted. So this is on our part again. There's thinking on multiple levels going on here, but essentially there's two different ways in which we think about thinking. We think about reasoning. So there is the embodied reasoning component, and then there's the interleaved reasoning component. So just as a high level, we have two models: the Gemini Robotics ER model and the Gemini Robotics Actions model. The Actions model is what we call the VLA, and that is mostly focused on short-term taking actions in the environment and breaking those actions down, and there is some thinking involved and so on. But then most of what we perceive as intelligent thinking is actually this high-level model called the embodied reasoning model, and I'll let Ted tell us more about it.
Thanks, Drew, for the clarification. Absolutely right, Drew and Sophia. Like this two-level system, I think, is quite important and represents, even how our team has tried to solve the problem of robotics. I think instead of just solving it from the robotics perspective on just overfitting to the data, so to speak, we've really tried to take the web scale frontier state-of-the-art intelligence of Gemini that understands, the world just as we do, and leverage that, because that's a lot of very rich priors. It's a lot of useful information. I think Gemini has, as a model itself, is of course very strong in many domains like code and math, etc. But an area where it has consistently excelled is multimodal understanding images and videos about the real world. With that as a starting point, what the Gemini Robotics ER model, embodied reasoning model, is just a further emphasizing and improving this physical world understanding knowledge of Gemini to make it a really great fit as a central brain that coordinates, a agentic robot system. Just as today you see the very exciting rise of digital agents, browser navigating computer use agents that are breaking down long tasks. To use your example, maybe on the computer you'd want to book me tickets to London, and it will, click web pages and do this whole flow. In the real world, you have a similarly and potentially even more complex and unforgiving flow you would need for pack my suitcase for a trip to London, which will involve, tool use of looking up the weather in London. It will need to understand your wardrobe, the items in it, and then map that to subtasks, a plan that the VLA can actually understand. What we see today with a lot of these VLAs, the models that Dhruv mentioned that actually predict low-level motor commands, any of this higher level reasoning, they won't understand, hey, if you gave me a very vague instruction to pack my suitcase for London, they won't know how to do anything. They respond very well to unzip the front of the pouch, grab the red jacket, put the red jacket in the bag, close the bag. That's the level they understand. And so you need a brain that can break down pack my suitcase for London into that level of granular detail and kind of monitor the system as it's going. And if the robot fails, knowing to ask again or retry. So I think it's a very pretty beautiful like twin of what we see happening in the computer and browser and digital space. We're trying to, have that same level of performance and utility for all people in the physical world as well. And the ER model, the Gemini Robotics ER model, and how it interacts with the Gemini Robotics VLA model is a very core component of that.
Would like to understand better how this ER model was trained, like what kind of data did you use, some like just more like if we can dive in more deeper, because it seems like it's like very important component of the entire system. It's like basically like that brain that gives commands to what task to do.
Happy to dive into that a bit, perhaps. Would it be helpful if I presented or
Yeah,
shared
sure.
my screen?
Yeah.
I can just navigate to the tech report. That it's the public tech report on archive that we're looking at, which is the same, I think, as the Google version. But this is the section 4 is where we deep dive into the Gemini Robotics ER model. I think I can share a bit maybe about, kind of the rough, like, what is it? How did we create it, and what does it do? And like, why is it interesting, potentially even beyond robotics? Here is kind of a plot where we showcase the philosophy we use when designing our model. We started from Gemini 2.5 family of models, which are extremely strong models for both the Flash and the Pro versions. And the big breakthrough there, this last year or so, I would say, maybe you're familiar with DeepSeek and GPT-5 and Gemini 2.5, is this idea of thinking, of using more test time compute, thinking for longer, getting better results. And what we were interested in is whether or not the fact that thinking can improve performance also applies to the physical world in a general manner. On the x-axis here, we measure the generality of different models. How well do they understand a broad spectrum of capabilities, from creative writing to code to graduate student level knowledge? And on the y-axis, we measured what we've been calling embodied reasoning, the ability of a model to understand the physical world, understanding space and time and contact and causality. We measured this a variety of ways with a lot of open academic benchmarks as well as internal benchmarks. But what we see here is that a lot of previous models, such as the main Gemini 2.5 models or GPT-5, are very general models, but for their ability to understand the physical world, their embodied reasoning performance, they're around, this is out of 100 on very benchmarks, so they're around 50% out of 100. And with what we did with the Gemini Robotics-ER model is, with a flash size, speed, and performance, we're able to improve the model to retain a lot of the generality that you'd expect from frontier models, while really emphasizing really state-of-the-art embodied reasoning that's substantially better than all other models that we evaluate. How did we do this? We used a variety of techniques and data and ideas from Gemini 2.5. We of course made a lot of adaptations. It's a completely separate model. What I want to emphasize is that the model, for the first time, at least my own experience, is the first model that I've released publicly, where anyone can use it today. With your own API key on AI Studio, anyone can query this model. And it's not only good at like robotics task planning, it's generally a model that's just very strong at understanding the physical world, at performing embodied reasoning. I think there I can pause there of like what this model is and how we did it, and happy to dive into detail anywhere else.
The physical world and the robot in the physical world has to deal with causality at a much deeper level than I would say these informational domains force us to think about that. I mean, a number of questions around that, but I was wondering if you've seen evidence that like active learning is more effective at learning these causal aspects than, say, imitation learning or training on videos. It's intuitive for people that, you sometimes have to get your hands in there and actually try things to actually learn about the subtle causality that occurs in the real world.
I'm imagining like an excavator moving a boulder, and the boulder's slipping down the hill and it's scraping against the excavator tooth. And to understand that and where the motors are at and why a boulder is sliding, but something else might slip through, or you wouldn't get that in a simulation necessarily.
I think intellectually, this is an extremely interesting question on like, is understanding causality and the effects of your actions upon the world, is this fundamentally different from like rote memory, like supervised learning of next token prediction on like a very passive source of data, like let's say a novel or something like that? I think it's a really fascinating question. It's, I think, why I and Dhruv and many others are interested in robotics, because this question is fundamental to, if we want to build embodied agents that are interacting with the world constantly. You don't get a redo, you cannot pause, everything is real time, every action you have in the real world has a consequence. Whether or not, imitation learning or active learning, whether or not simulation or real data, I think is appropriate to solve this. I think the jury is still out. I think you can get very far with supervised learning, with imitation learning. I think it's clear from frontier models with emerging capabilities that oftentimes what we as humans, as researchers, think, oh, we're gonna need X something else to solve this problem, the scaling effect of, you know, an internet scale of data of what these models have fundamentally learned, the implicit representations, the priors they've kind of consumed, oftentimes surprise even the researchers. While I think the idea that like you know, an active continual learning agent out in the real world learning tabula rasa, if you guys have seen like Rich Sutton's new Dwarkesh interview about like goal-oriented learning, I think this makes a lot of sense to me. At the same time, I think I would not discount the fact that large scale robot data efforts and deployments now, as we're starting to see with various companies and even consumer robots like 1X, like maybe you can still get a lot of the benefits of that truly continual learning agent while still leveraging the unit economics of something that's a bit more scalable, where you have stage collection, deployment, and training. I also want to caveat that this is my own belief as someone who thinks about robotics, you know, a lot, not necessarily that of Google DeepMind. But I think it's a great question, and it's an open one in my opinion.
I'm wondering, like, since we're talking about continual learning, and when I was reading your bios, I noticed, like, in Dhruv's bio, Dhruv mentioned that he's also like continual learning is like part of his research. I was just like wondering, like, what's happening in continual learning, and it seems like it's still like very deep research area.
There's a lot of things to be done, and I just wanted to kind of follow up on what Ted said. In some sense, like the type of research that we are in, research landscape we're in now in broader AI, but also in robotics, is in some sense very slow iteration cycle research. Because, you know, for instance, if training a model takes a week and then evaluating it thoroughly and understanding, which by the way is a whole train wreck, we have this whole thing to figure out, which is what makes a model good and bad. And you do that, and then you understand what works and what doesn't. If that iteration cycle takes, you know, even a few days or a week, as opposed to you write some code, you get some output, and then you debug it, it means that we are not able to try out every possible idea. So a lot of the ideas that Ted mentioned, and as the audience said, everyone is kind of on their own exploration chain. Each company, each lab, each academic lab, each startup. So a lot of the things that you will hear us say and other people say will differ mostly because we made different decisions at some point in the past, and we are now trying to follow up and understand what those mean. And at some point, everyone will backtrack and align on something that agrees. But it is early. Like that said, a lot of the things that we do is banking on supervised learning as the base capability, kind of following up on what's been working in the big model landscape for language and vision. But if you want to take a page from, you know, from the VLM playbook, at some point we will, you know, reach the point where supervision teaches you enough foundational knowledge, enough exploration priors, enough to get started, and then comes the real world where you're thinking about learning on the job, kind of online learning, trying to steer your models. That's where kind of continual learning fits in again, where you're thinking about either iteratively improving the model with interaction in the environment. That could look like reinforcement learning. That could look like, you know, iterative supervised learning. And we are scratching the surface. We are, you know, certainly working on it as a team and as individuals. But what form it takes will very likely, you know, be determined by how good your base models is, your base models are right now. We'll have more to share, kind of, you know, in a few months when we are more certain of what we're playing with. I do think it is a very interesting time to be thinking about these problems, because we're finally in a place where the base models, the pre-trained models, actually work. Between March and October, which is when, you know, our two releases happen, we went from models that can do something on a set, you know, fixed set of environments that it's seen before, to models that can actually do something in new environments. Something which we haven't covered so far yet, but we've been taking these robots out. We have these models. We take them to conferences and shows, and we open to thousands of people that attend there, and people can come to the robot and put objects in front of the robot and ask it to play with the robot. So we've had a lot of these experiences with people. The two things everyone says is, one, oh, it's not that good. The second thing is almost always, we expected it to be way worse. No, you know, if you take a wallet out of your pocket and you put it in front of the robot and you say, take a credit card out of my wallet, it's probably not going to get it. But the fact that it's so close and everyone's cheering for it kind of shows you that it is at a point where the pre-trained model is almost good enough to start improving it very slightly. It's at the point where a small amount of specialization, fine tuning, adaptation, continue, whatever word you come up with. But a small amount of learning is going to be enough to, to teach it something very personal and that actually works in the real world. So I think that's kind of where we are, where we haven't been thinking and talking too much about this learning on the job enough. But I think we'll hear a lot more of that, because that is kind of a key piece of getting these robots actually close to people and interacting with people and doing meaningful tasks.
Maybe put a suggestion consider for an interesting experiment. This is kind of getting back at my previous question, but it'd be to train a robot to juggle in two ways. One way would be passive, have to watch many, many videos of juggling and see how long to learn how to juggle through imitation. And the other would be to do it actively, have it practice juggling and correct. And it'd be super interesting to compare the speeds of learning on those two. I know for myself, I could watch a million juggling video, never learn how to juggle, but yeah. So, and it would make a really impressive demo as well. I also meant that I think the idea of I guess federated learning, I guess is what I would say it, once we get many, many, many robots out there, seems really, really promising. And I mean, it's kind of what you're talking about with some of the real worlds and transfer learning here from different robots. But once they become widespread, that seems like that would be the way to really accelerate data. So
100%. I think a lot of these ideas have been prominent in the different waves of robotics, and I think they will again come back in this new wave, which is the VLA wave. I think maybe 5 to 8 years ago was the small models but end-to-end learning wave of robotics, and a lot of these did kind of come in. I think a lot of the work from our team, but also other people in the community, has been around active learning, about reinforcement learning, both online and offline reinforcement learning, and learning from feedback and human cooperation, and robots teaching other robots by watching them, and deploying fleets of autonomous robots. We've done a lot of this in the past, and we have seen that the value of learning on the job, it only matters after you've solved the first 60% of the boring stuff. But then it is the highest marginal utility you can get from kind of time spent by the robot in the real world. I think in the new wave, maybe it's like a little bit early to start talking about these things, but it will surely happen, where once we understand how to train these models at scale in a stable way, and how do we fine tune them without losing their base capabilities, we will kind of see a resurgence of all of these ideas that you mentioned.
If I could also maybe add some more context, Lonnie, a really great question, by the way, is I realize there might be overload in the word imitation learning. In what I think oftentimes we robotics researchers think of imitation learning is very different from the social cognitive neuroscience version of that word, which I think looks like observing other people do it and then trying to copy them, learning from videos. And I think you raised a great point that while you can watch millions of hours of a professional playing tennis, maybe nothing actually beats go and trying it yourself. And I think how we train robotics today actually looks a lot more like mimicking the actual low level motor commands. So it does look like, maybe imagine you're taking a tennis lesson from a professional, and they're like manually guiding your limbs into the right appropriate amounts, and it looks less like watching passive video. So I think that's where the terminology actually means almost opposite things of how we've been referring to it. But I do think that, like, even within imitation learning, right, supervised learning, we collect the offline data set. What does that look like? It looks like humans piloting robots, showing them where all their joints should go in real time, oftentimes either with VR controllers, or what we found recently actually is that even the VR controllers have an embodiment gap. The controller is simplified, and when you map the kinematics onto the robot, there could be differences. So in fact, what everyone in the field has done, maybe for the past 2 years, is actually get closer to this kind of like direct imitation of the lowest level joints by mapping there's basically a twin. There's the robot that's actually doing stuff in the world, but there's a twin of the exact same robot that pilots teleoperators will actually move. And this is called puppeteering. You have a robot that's puppeteering and cloning into another robot that's actually interacting with the world. But this gives you high quality data and is a way for you to directly teach the student robot exactly what to do. In the future, however, I think, but the reason that I think this is the status quo is it's very effective, but it also may not be scalable. So I think directionally, we actually want to go more in the direction of being able to learn from cheaper sources of data, like watching videos or learning from other robots. But right now, that's an open question. So the current default is actually almost exactly what you suggested of learning the direct low-level motor commands directly.
Actually, as a side note, we did host a researcher who worked on Le Robot and also Aloha researcher. I dropped links if guys on this call interested in like watching those previous talks, feel free to do so. At least I remember, in the past when I spoke with robotics researchers, that reward hacking seemed to be like a big issue in robotics. I'm just wondering, how is it now? Is it like still like one of the like main challenges in robotics research?
There's been a lot of work, especially in simulation, when we try to leverage simulation at scale, trying to align sim and real. And there's a lot of different ways in which you need to align simulation and real. But one of the challenges, kind of, there's the physical fidelity, there's the visual fidelity, and then there's kind of the realism of feedback, which is where reward hacking comes in. Personally, both Ted and I, we don't quite work a lot on on leveraging sim itself. There are people in our team that do, but we have been thinking about this in the context of real world learning, and eventually when we get to reinforcement learning in the real world. A lot of the interesting advancements outside of robotics that could be really helpful right now has been around using verifiable rewards, using human rewards, using models, kind of machine supervision, and so on. And I think this is something we are quite interested in and actively kind of developing. So some of the capabilities of the ER model that Ted mentioned, like success detection, like sub-step prediction, like if you can have this general VLM tell you how successful a task has been, in some sense, that is a reward model now. Whether that will be good enough or whether that will be hacked by an agent learning in the real world, I think only time will tell. But certainly, the generalist view on better reward models has been to try to do this at scale, starting from general purpose VLMs and trying to get these interesting signals out of that. So yeah, I guess we haven't been thinking too much about real world reward hacking just yet, but yeah, I'm sure this has been studied in the context of VLMs and language models. And as we talk about agency in the physical world, just like agency in web agents, for instance, I think a lot of these problems will come back and we'll have to deal with them.
To some extent, it's like alignment problem, right? And since some language models, they also not always behave the way we expect, and since like we're using them as a core for robotics, the same problems that we see with language models probably translate to robotics as well, right? To some extent.
That's right. Yeah, I don't think it'll be the only way to like the only solution or the best solution, but certainly I think one of the thesis we abide by has been scaling, and I think in the scaling way of thinking, I think a lot of these problems they have been studied already, and we will try to follow these playbooks, and there will be things that will be unique to interaction in the physical world. And I think the sooner we get there, the more interesting research there will be in robotics.
I think, I came to a session not long ago, and I've seen a lot of companies and teams building robots that are creating data collection pipelines and also proposing, I guess, similar models as Scale AI and some of the other data companies. What are some of the constraints with sourcing this data or collecting such data? I think, when I went to see one of the robot gyms, for example, I saw that a lot of these robots and the teleoperators are constrained to a particular configuration of the robots and the tasks to perform. I was just curious if you guys can elaborate or share some of your thinking around that.
I think it's really exciting. And I think also like robotics researchers, we also see like a dozen new robot data foundries starting up every single week, both startups and like agencies or whatever. I think it's interesting, right? Because I think it's predicated on the belief that I mentioned earlier, that robotics and internet scale of robotics data is going to be necessary. Maybe not sufficient, but it's going to be necessary. So this data will be very valuable. Sell gold in a gold rush, become the scale or surge of robotics. I think this is a very exciting vision, but at the same time, I do think that the constraints you mentioned may have very drastic consequences for the trajectory of like the value that the data these companies provide can give. I think in my view, kind of what does it take to collect useful, high quality, scaled robot data that will be guaranteed to be useful not only today, but in the next few years? I'm not sure. I think if you look at what works for Scale and Surge for collecting, let's say, hiring graduate students to kind of write high quality code or to answer like, math proofs, like that data, once it's high quality, is almost always going to be useful for post training language models to do amazing stuff. But in robotics, I think because there are so many interesting questions of like, what is good data? What is the right robot embodiment? How should you collect it? Do you collect human data, like with egocentric, like wearing a GoPro? Do you collect teleoperated data? Do you collect it on a humanoid, or do you need to collect it in like the factory you need to deploy on? All of these questions, I think right now the jury is still out. And I think just going on past experience, there has been actually a lot of data collected in the past on many robotics projects in academia and industry, but most of these data sets have had like a half-life of one project. It's useful for answering one research question on one project, and then the utility of that data almost drops to zero. It's just not useful for the future. And there's so many things that can make the data just fundamentally too constrained. Maybe it's too suboptimal. It has too many, maybe the task is too narrow. Maybe it's missing importer sensor data, or maybe even just the strategies used to collect it was not suitable for what you want to do next time. I almost, equate it to like if someone says they can sell you, 1 billion hours of tennis video data, but the data you actually needed was, the teleoperation, a coach to teach you how to play tennis. No, perhaps there's, even if someone says I'll give you 1 billion hours for really cheap, or I'll give you 1 trillion hours, maybe what the data you actually needed is very different. And so I think that's a risk. May not be a fatal risk. There will be startups that figure it out correctly. Maybe the research will advance enough where these data foundries and the constraints won't be fatal. I think it's an area that's extremely interesting, and there indeed are a lot of startups in SF doing it, and we're watching them with interest. And Google DeepMind has our own big data plays in house, but I think everyone on the team and the community is excited about how to get 100x more data, 1,000x more robot data in the coming years. That's a really big question.
So I recently got into look into VLAs and VLMs. I noticed that the robot and the other models, they don't consider things like tactile or mechanical feedback. Is the Gemini Robotics team looking into that? Do you feel like it's not even necessary to have that kind of feedback and instead just have visual feedback?
The standing question here is, at what stage of training would new modalities need to be introduced? It's widely agreed that tactile is an important modality, and a lot of smart people are working on it. I think perhaps the simplest answer to why we don't see kind of tactile foundation models as much is the scale of data is not quite nearly as much as image and text modalities for these kind of foundation models. There's been a lot of academic research on how we can staple these new modalities as a post-training step. So you start with VLA that was trained without some of these modalities, and then you add that capability on later. And it seems like it's helpful, which means it will start making its way into more industry and startup foundation models at some point. But so far, I think, yeah, it's mostly trying to understand at what scale do we want to add these modalities, at what stage do we want to add these modalities, and what the right way to use them is. For sure, at some point, all of these models need to have it. I think it's just early to tell exactly in what form they will exist.
In the evening, at night, and then you're operating in the day. In the day, you have shadows. At night, you might have low lighting. Things might reflect differently. So do you try to account for any of that before you encode the model, or is that all you just have to have it at night and during the day so that it can understand? Do you try to identify different objects, any techniques that you apply to overcome those issues?
At a nutshell, I think that's kind of the beauty of the approach that we have been pushing at GDM, which is data-driven learning-based methods, which you like ideally it's not scalable to encode each of these into the model design or into specific modules from the start. Like you'll never be able to just iron out all of these edge cases. And so what we've done is by collecting diverse data, by training on an internet scale of data using a strong backbone like Gemini, which is already invariant to Gemini, has seen photos of dark and light rooms. It's seen these kind of lighting changes. It's aware of environmental factors. It scales to cameras with different intrinsics and extrinsics. It's seen iPhone photos. It's seen robot camera images. We're leveraging Gemini's robustness in order to get that transfer and robustness to environment factors for robots for free almost. And we found that this works very effectively. Gemini Robotics is state of the art in how it can generalize to visual distribution shifts under these conditions that you mentioned.
Recently, I spoke with a researcher and he said, like by his estimate, where we are in terms of robotics, it's like GPT-2 era. It's kind of, we see like something is working, but like it's not like, as like mind blowing as we saw like with, I don't know, like Gemini models or GPT like 4.4. What do you think about this estimate? Like actually, what do you think where we are today with robotics? Like if we take that scale of, if we use the LLM numeration.
Once again, this is only my personal view, but I think GPT-2 or GPT-3 is a really good kind of estimate of where we are now, in my opinion. I do think like the hype in the demos that you'll see today make it feel like we are in the 2022, 23 era, like GPT 3.5, ChatGPT era of robotics. But I think where the technology is objectively is probably closer to 2020, 2021. So I think there is some gap, but we start to see models that too many inputs of initial condition, robot, and instruction can give you something reasonable. It may not take the credit card out of the wallet, but it will try. It will go to the wallet, it will try to open it, and it kind of knows. It's like a toddler. Maybe it doesn't have all the dexterity or the mastery ready yet, but it's at least trying to do the right thing. And I think when that generality goes up one notch and the performance goes up one notch to be like minimally useful in a universal variety of scenarios, I think that's a very, very exciting moment. And that might come, in the next few years.
Do you think in our lifetime we will see like humanoid robots as like it was on Westworld, that like to that level of, that it's like kind of real human? Do you think it's possible in our lifetime?
The technology to do that, absolutely. I think a few years ago, there were debates of like, will this ever happen in our lifetimes? And now the debate is it going to be 5, 10, or 20 years? So I think that's extremely exciting. Like, will it ever happen? It's definitely happening, just when, I think. And I fully believe that. Whether or not it's going to look like Westworld and whether it's going to look like humanoids, I'm still not sure. I think humanoids are a very interesting research platform. Our team at Google DeepMind is working significantly on humanoids, but whether or not, for economic and product market fit reasons, whether the world will be filled with humanoids, I'm not really sure, or whether it will look more like vacuums and microwaves and fridges and cars, where you have purpose-built machines that can be economically scaled. I'm not sure. And again, I don't think Google DeepMind has an official comment on that. I personally also am not sure. But I think the technology, the autonomy, the hardware, the software, it's going to get there within our lifetimes. Absolutely.